Hello, people of the internet. I want to give you a quick introduction to data structures and algorithms, starting first with what you should prioritize in a data structures and algorithms class, working through an example in data structures and algorithms of searching for data, an improvement upon that, which is binary search, as opposed to just a simple linear search, exponents and logs, and then a really brief high-level intro into the basic ideas behind Big O and why it's important. So to start off first, programming priorities, like what should you be worried about when you first start programming? The obvious thing maybe is that your program should be correct. And then the second thing that a lot of people think about is usually how fast their program is. And usually they think of speed purely in terms of the literal amount of time, like the actual time it takes for my program or my function to start and then stop. But in data structures and algorithms, we want to focus on something that is still speed in a big way, but isn't measured in terms of, say, the number of seconds or how long it takes, but is measured in terms of how much longer it takes as the size of the problem or input gets larger. So let's move right into searching. So if you're working on anything, right? Say for example a database, or maybe you're searching online for something and you want to get results really quickly. You can imagine that a company like say Google or Bing, right, has a ton of search results to look through, and when you search for something, they could write their code so that it literally checks every single web page that they've downloaded and looks for whatever you're searching for. So if I search for apples and bananas, then it's going to go through every web page that it's downloaded and see if the word apples appears in it, right? That would take forever. If the number of web pages doubles because there are just more web pages now, and somebody runs the same exact query, now it's going to take on average, twice as long. In fact, it's guaranteed to take twice as long if you're searching for everything, right? If I have twice as much stuff to look through and it still takes me 1 millisecond for every web page I look at, now it's going to take 2 million seconds, and so on and so forth. And so, in this way, searching through things one at a time is linear. And by linear, we mean that if you plotted the relationship between how many things you had to look through and how long it took, you would get a line. So to draw that out, right here we might have time, and here we might have, say, the number of things you're searching through, and I'll just call that n for now, n web pages. And maybe there's a small amount of time that the program always takes, or that my function always takes initially. So even for 0 documents, there's some amount of time that it takes. But then after that, it's basically going to be a line. And so if I have n documents and I double n, then I'm also going to roughly double the amount of time. If I have 10 times as many documents, now it's going to take about 10 times as much time. So, not very good. But we can do better. Let's talk about searching within a particular web page. If I'm looking for the word apple and I just want to know whether or not it's in the web page, I might have a list of words in that web page and search through that list of words one at a time. And again, we have the same exact kind of thing if we take that approach. Without doing anything special to the web page, just looking word per word, if I have twice as many words, it's going to take twice as long to search through that web page. So the first thing we can do to make an improvement is beforehand take the web page and actually sort all of the words in it, and then we can apply binary search. So the problem initially was that we couldn't really tell if a word was inside the web page unless we actually looked through the entire web page. Right? There's always this chance that the word apple could be the very last word that we look at, so we have to look at every word. But if we sort it, that's no longer true. In fact, let's say we're looking at a web page that lists all of the fruits. So if we have, say, a really small list, just apple, banana, coconut, and dog, you can imagine that this list goes on and on and on, and maybe even has 1,000 words. If we start out with the list sorted, then we can take advantage of that, right? If we're looking for a word like apple, normally if we have this huge list of words and it's not sorted, any one of those words could be apple, or apple might just not be in the list of words at all. And the only way to know is to look one by one. There's no way to narrow down except to look at every single word. But in binary search, what we can do is just take a look in the middle. In this case, maybe let's look at the word coconut. So if we're looking for the word apple, and we start with the word coconut, right away we know that apple must be less than coconut because it comes first in the alphabet. So right away, we don't have to look at half of our list of words anymore. And you can repeat this step. Now if I look at the word banana, it's the same exact thing all over again. Now I can know that the word apple isn't going to be later than banana. It has to come sometime before. And then I find it. But let's think about what happens when you have a huge, huge list of words. Let's say that each of these little buckets is maybe 100 words. If I'm looking for a word like, I don't know, melon, right? I might decide to start in the middle. And just to make this a little bit more concrete, let's say that there are 1 million words. And right here, we're looking at word 5,000. But the cool thing about this, right, is even though this extra step of looking in the middle and checking is a bit more complicated, for every one of those steps that we do, for every cutting in half and checking the middle that we do, we eliminate at least half of the possibilities, which is crazy. Like, it's crazy how much faster it is, right? You know, right away at the very beginning, we started off with 1 million possibilities and we can immediately get rid of about 500,000 of them. Even if the word we're looking for isn't in our list of words, every single time we look, we cut the whole list in half. So I might start here. Maybe this word is cantaloupe. And so if I'm looking for a melon, I have to look somewhere to the right because I know that the word melon is greater than cantaloupe. Now I know that my word is somewhere between 500,000 and 1 million, and I just cut it in half again. About 750,000. And I can keep repeating this process. And the cool thing is, no matter how bad the situation is, no matter how unlucky I am at guessing, or if the word just isn't there at all, every single time I look, whether I have to go left or right, I cut everything in half. And so this kind of raises a question now. You know, what's the worst case scenario? Earlier, if you have to look at every single word, if I double the number of words, now it takes twice as long. But in this case, I'm always cutting in half. So if we work our way backwards and think about how long it took to get through 1 million words, kind of realize that, hey, if I had 2 million words, I would have checked right in the middle. And immediately I would have been able to get rid of 1 million of those 2 million words. So every time I double the amount of input, every time I double the size of this problem, it doesn't take double the time, it doesn't take twice as long. It only takes one extra step. Admittedly, that step is pretty complicated, but it's still just one step. In fact, now I think it's a good time to talk about exponents and logarithms. So think real quick, if you have a number of words, how would you figure out how many times you can cut that number of words in half until you get down to just the last word? First, let's talk about powers. We're going to get to how many times you can cut something in half, but I'm going to start with something a little simpler first. So you might remember from grade school that multiplication is just repeated addition. Similarly, powers are just repeated multiplication. So if I have something like 2 times 3, this is the same thing as 2 plus 2 plus 2. Similarly, if I had 3 times 5, this is just 3 added to itself 5 times. And there's a very, very similar thing that happens with powers. So if I had 2 to the 3rd power, that's just equal to 2 times itself 3 times. And that ends up being equal to 8. Let's work through 3 to the 5th power. Just 3 times 3 times 3, 5 times. And if that wasn't super obvious, definitely don't worry about it. We have calculators for this sort of thing. It's just important to know what a power is, not necessarily to be able to calculate it really quickly in your head. Sort of how division is the opposite of multiplication, and the order of, a divided by b matters. A logarithm is the inverse of a power. So to work off of this example, let's ask ourselves, how many times could I divide 243 by 3 before I get to 1? So I have 243, want to divide it by 3. Turns out I can do that 5 times. And the way to think about that is to look at all these 3's multiplied by each other and realize that this is just 1 times 3 times 3 times 3, right? It's the same thing. So what I can do is I can just take 243 and I could divide it by each of these 3's until I have 1 left. The way we write this is to say the log base 3 of 243 is equal to 5. I can cut 243 into a third 5 times before I get to 1. And the same thing happens with other powers too. There's nothing special about 3 and 5 or 243. If I take the log base 2 of 8, I get 3, because I can cut 8 in half 3 times before I get to 1. So bringing this back to binary search, if I want to know how long binary searching through n words will take, I just have to take the log base 2, and that'll give me a pretty good idea. In particular, if the size of my input, if the number of words I had to binary search through grew by 8 times, then there would only be 3 extra steps required. Try to think about how long or how many steps it would take if you had to binary search through 1 million words. The answer is only about 20 steps, whereas if I was doing a simple linear search, I'd have to do 1 million steps. Even though those steps are faster, it's still 1 million steps. They're not 1 million times as fast, so it's a lot slower. And this really gets into why we care about big O in data structures and algorithms. We don't just care about the raw speed. If you're able to process, 1 million words really, really quickly, like 5 seconds faster than the other person's program, so maybe your program takes 1 second, but their program takes 6 seconds. That's pretty cool, but if your program takes linear time, doubling the size of the input means taking twice as long, then pretty quickly your program is going to become a lot slower than someone else who's able to do something cool like binary search, where doubling the size of the input doesn't double the time, but just adds 1 extra step. And that's it.